Hi, my name is Kai, and this talk is about a new SSSP algorithm on GPUs. Let me give you an introduction first. A single source shortest path is a well-studied graph problem with many pair solutions, and our solution is a highly performant GPU algorithm for diverse graph types. Where we achieved 2.88x average speed up for 226 graphs against the previous state of art. And this is achieved by a sophisticated yet efficient work scheduling algorithm. So the goal of SSSP is to find the shortest path from the source vertex to each other vertex. For example, here the source is A. And we also keep a per vertex variable called tentative distance, which represents the currently best known distance for that vertex. Initially, the source is set to 0 because it's the source, and all others to infinity because the other vertex are known initially. And step by step, we update the tentative distance. For example, in the first step, use vertex A, use its own distance and the H weight to update B's distance. Now, the next step, B's distance is known, so it can update its neighbors, and so on. But notice here, at this step, B have two neighbors, C and D, so which one should we update first? This is part of a work scheduling problem. And there are two well-known algorithms that does this differently. One is depth trust. Depth trust uses a priority queue to determine which vertex to process next. So at each step, we insert neighbor vertex IDs and use tentative distance as case. For example, here, B inserts its neighbor C and D, and because C have a shorter distance, so it will be ordered in such way. And we always dequeue from head to update. So you can see because of this, C will be updated first than D, and so on. So the key point here is vertex updates are ordered by distance, and we update each vertex exactly once during the entire execution of the algorithm. And another algorithm is Bellman force. So it uses list instead of priority queue. And because of this, the vertex update in arbitrary order. And because of the arbitrary order, so each vertex may be updated multiple times instead of just once. So it may end up doing more work than depth trust. For example, here, so you can see vertex D is updated twice. First, it's updated with distance of the path A, B, and D. So clearly, this is not the shortest path. So it must be updated again with A, B, C, D. So clearly, the first update is a useless work. And furthermore, if we update D with the longer distance, so D may use this wrong distance to update its neighbors. As you can imagine, if we have a larger graph and if we have many threads working parallel, we end up have a lot of redundant work. In general, there are three different trade-offs between different techniques. First is work efficiency. That means how many vertices that are updated during the entire execution of the algorithm. And secondly, concurrency. That means how many vertices can be processed in parallel at any given time. And third is the overhead of a work scheduling mechanism itself. For example, priority queue versus a list. Depth trust and Bellman force basically occupies the two ends of spectrum in each category. So in terms of work efficiency, depth trust performs least amount of work. In terms of concurrency, because depth trust have to process vertices in exact distance order, and the priority queue is very difficult to parallelize. So it's mostly a serial algorithm. While in Bellman force, because vertices can be processed in arbitrary order, so all the pending vertices can be processed in parallel. And finally, of course, the list is much simpler than a priority queue. And now the question is there something in between? And the answer is yes. There's another algorithm called data stepping. So data stepping is basically a midway between depth trust and Bellman force. So essentially, it enhances Bellman-Force with the proximal ordering to have better work efficiency. And unlike that trust, it doesn't process vertices in exact order and doesn't use periodic queue, so it's more parallelism friendly. So let me demonstrate how it works with a simple example. Let's say we want to insert A, B, C, and so on into the scheduling data structure. And the scheduling data structure for data stepping, it's a number of buckets. So each bucket is a list. So and we want to group those vertices into bucket. So the meaning of data is the granularity of each bucket in terms of distance. For example, if we chose data to be 100, the first bucket will accept vertices with distance from 0 to 99. So A and B are put here, and so on. Vertices within each bucket can be processed in arbitrary order. So there's no ordering, and the buckets are ordered. To implement data stepping, originally this is proposed for CPUs, and later on it's adopted for GPUs as well. The current state of art is also based on data stepping. So the key issue to implement data stepping on GPU is we must make the data structure scalable, because GPU has 10,000 threads. So it must be relatively simple and have a lower overhead. So that's how the focus of a previous algorithm. But as a trade-off, it have negative impact on work efficiency and concurrency. So our solution is also based on data stepping, but we want to use a more sophisticated work scheduling mechanism so we can have better work efficiency and concurrency. And we want to make this complex scheduling technique scalable for GPU as well. Now let's talk about the first issue here, how we can implement multiple buckets. The problem is those buckets grow and shrink in size during execution. So at any given time, generally speaking, work items are distributed non-uniformly into buckets. So some buckets may have more work, some buckets may have less. And furthermore, the number of work items in each bucket also changes over time. So that means it is impractical to implement those buckets as a fixed size arrays because you use too much memory. To solve this problem, for CPU data stepping, each bucket is implemented as a linked list, so it can handle this kind of sparsity in bucket usage. And clearly, linked lists are not suitable for GPUs, so we need an array-like data structure. And because of this reason, previous GPU data stepping use just 2 buckets instead of many, so that they can implement those buckets as fixed size arrays will put an upper bound on memory usage. And the downside clearly is less work efficiency because the 2 buckets have a less process ordering. So we may end up doing more work. So the goal of our solution is we want to use many buckets, and we want to find a way to implement buckets as array data structure as well. Now let's talk about the second issue. How do we implement those buckets as a concurrent data structure? To simplify discussion, let's assume only a single bucket used. So one way to implement a concurrent data structure is to make them multiple reader and multiple writer. So basically, it means we only have a single buffer, and these threads are allowed to read and write the same buffer. So the problem with this approach is that a lot of synchronization is required to avoid this condition. First, we need synchronization between writers to ensure they only write to unique locations. And second, we need to have a synchronization between reader and writers so that readers only read out valid location. So that means the location has been fully written to the memory. And third, we need the synchronization between the readers so they can read unique locations. That's a lot of synchronization. And because of this reason, previous GPU data stepping use double buffering instead. And this is also how the concurrent data structure are typically implemented on GPU as well. So basic idea here is we use 2 buffers to implement a single logical buffer. so that threads only read from one buffer and only write to another. So for example here, D, E, and F is written to the write buffer, and we must read them out somehow. To do this, we use a global barrier. So we wait for all the threads to finish execution and all threads to finish written to the buffer. Then we swap the two buffers. So the old write buffer becomes a new read buffer. So we can read the data out. And we continue the process until the algorithm finishes. So basically, we execute this algorithm in iteration by iteration, and each iteration is separated by a global barrier. So the advantage of this approach is now the reader and writer operations are separate to two different buffers. So we don't need like a synchronization between reader and writers. I won't go into details, but basically, if we use this approach, only writer-writer synchronization is required. This in contrast, multiple reader, multiple writer need all three types of synchronization. And of course, there is a trade-off. So the problem is double buffering is reduced concurrency. For example, here you have a D and F written to the buffer, and we have some available threads, but we cannot schedule D, E, F because they cannot be read out. That's because they are in the writer buffer right now. And the whole point of double buffering is separate out the read and write operation. And to schedule D and F must wait for the next iteration. That means we must wait for all the threads to clear a barrier and mean for the buffer to be swept. So that's a lot of latency here. And while during this time, we have threads being idle. So we have a hardware underutilization. And in practice, we may end up have like many iterations, while with very little work in each iteration. So it can be a problem. And more generally, if we process algorithm iterations and separate by global barrier, this is also known as a bulk synchronous parallel. In contrast, if we use multiple reader, multiple writer approach, we don't have this problem because as soon as a work item is fully rented to the buffer, it can be read out and scheduled. So you have a better concurrency. And more generally, this approach is asynchronous. So that means we only have a single iteration and there are no global barriers used. So the goal of our solution is to use this multiple writer, multiple reader approach so we can have a better concurrency. And of course, the problem we have to solve is we need to find a way to reduce synchronization and the overhead so we can make it efficient for GPUs. The third issue is how do we choose a suitable delta value? For example, if we increase the delta from 100 to 150, we end up having more concurrency because we have more work in each bucket. But at the same time, we have less ordering, so that work efficiency is decreased. So essentially, delta controls the balance between concurrency and work efficiency. So what delta gives the best performance for a given graph? This to determine this is essentially to find out the optimal trade-off point for the graph. So it can be a complicated answer. Unfortunately, pair solutions use very simple heuristics. So that is true for both CPU delta and GPU delta. And they often choose far from multiple delta value. To summarize the difference between our solution and the pair solution, we want to use many buckets so we can have a better work efficiency. And we want to use multiple reader, multiple writer for better concurrency. And finally, we want to choose a near optimal delta, which affects both efficiency and concurrency. In order to do this, we need dynamic arrays with memory management. And we need to handle more synchronization and more overheads. And finally, we also need a runtime mechanism that can gather information and adjust the data. So we end up with a more complex design. And to cope with it, we use a technique called Carbon Delegate. So the basic idea is we decouple a single kernel into two kernels that with different functionality. So the graph processing kernel that handles vertex update. So basically, that's the main work of a single source shortest path. And the manager kernel handles work scheduling. And those two kernels running simultaneously on the same GPU. So essentially, this manager kernel is a delegate that handles work scheduling on behalf of the graph processing kernel. So that's why our solution is called decoupled delegate. We launch a single thread block for the manager kernel, and we use the remaining hardware threads for the graph processing. Within the manager thread block, we have three different verbs that each with a different task. The probe verb and the assign verb are used to handle multiple read, multiple write operation. And the verb handles memory management for the dynamic arrays. And the assign verb is also responsible for setting the data value. So the key point is we break a complex problem into smaller tasks, and we want to centralize the task instead of letting all threads handle everything. To support multiple writer, multiple reader buffer, as I mentioned earlier, there must be following synchronization between writer and readers for wide risk condition. And on top of that, there's also scheduling overhead. For example, we have to figure out which bucket is the head bucket and when to switch the head bucket, so on. In a traditional non-decoupled approach, all threads are responsible for work scheduling on top of processing the graph. That means they must perform those work scheduling related tasks in a synchronized way. So individual threads must pay the overhead for each time when they read and write the buffer. And also, the synchronization is required between all those threads. So in a decoupled approach, that is our approach. The workers only have to perform writer to writer related tasks, while all other tasks are centralized to the manager. So that means the manager can amortize those overhead. It means it can pay the overhead once for many read-write operations. And also, because this task are centralized to the manager, they also have a reduced synchronization. To support the dynamic data structure, our key idea is to use a customized memory management scheme for FIFOs. Here's how it works. Each bucket is an array without pre-allocated memory. And we have a single pool of allocated memory shared between those buckets. So our goal is basically reclaim and assign the block's memory based on the actual bucket usage. So each bucket is used as a circular FIFO. So we have a read and write pointers, and they all move in the same direction. The manager verb simply check the pointers to do memory allocation and deallocation. For example, when the write pointer increments, that means we need more memory to hold data, so we allocate the new block. So when the read pointer increments, that means an old location or has an old FIFO location has been already read out, so it's no longer useful, and we can reclaim the old block. The key reason we use FIFO is because it's a FIFO access pattern makes the memory management very easy. First, the pointers are always of monotonic increments. So that means it's very easy to figure out which location will be read next. So you can basically check the read pointer to allocate. And it's also very easy to pre-allocate. So we can basically pre-allocate a few blocks ahead of the read pointer, so we can avoid the allocation latency completely. The next property is that each location is read and write exactly once. So that means it's very easy to figure out which location can be safely reclaimed. We never have to worry about a location that will be used again because I use it exactly once. That means there's no eviction or spill space associated with a more general dynamic memory scheme. The final piece of solution is setting data dynamically. So we have this assign verb is responsible for assigning work and checking on worker status. So it knows the current level of GPU utilization. And we can use the utilization information to adjust data to try to get a GPU fully utilized. So that makes the assign verb the natural candidate for setting data. We know the following. So we know how many hardware threads for given GPU. And we know how many work items are currently being processed. So each of the work items is a vertex. And we know the average degree of the graph. So this have two use here, the average degree. So the average degree is basically correlated with the amount of work for each vertex. That's the first one. Next one is from the average degree, we can have a basic idea of the level of memory divergence. So based on this three information, we can estimate a hardware utilization level. So with consideration of both the hardware threads and the memory bandwidth. To use the hardware utilization level, the basic idea is to avoid underutilization. So that means the amount of concurrency is roughly available to the amount of hardware resource. So let's say we define a fully utilization point here. And we want to define the low utilization threshold and high utilization threshold around the full utilization point. So let's say if we detect that we have a hardware underutilization, that means there's no need for further work saving because the hardware is already idle. So we can increase data to get more utilization. And let's say we are in a range of beyond the high utilization threshold. That means that we have more concurrency than needed. So we can decrease data to get work saving that will give us better performance. So it's basically we do this periodically and repeatedly, so we can trap the current data within this range around the full utilization point. This is the optimal point to give us a better performance. So that's basically how it works. Now let's talk about the results and the evaluation. We use 226 graphs from Lone Star benchmark and the sparse matrix collection. The reason we use so many graphs is because the work saving and the concurrency have a very different effect on different graphs. So we want to make sure our solution works for diverse graph types. We do our experiment on the RTX 2080 Ti GPU, and we also evaluate 7 previous GPU solutions. And this table shows you the average speed up of our solution versus the previous solution. That is average over 226 graphs. So you can see the Lone Star 4.0 is the best performing one for the previous solution. So this is the state-of-the-art GPU solution that you data stepping talked about previously. And our other solution are either variations of Bellman-Force or data stepping. We also evaluated 2 other state-of-the-art CPU solutions, both multi-threaded and serial. And this is on i9 10-core CPU. So against the multi-threaded data stepping, our solution achieve 15x speed up, and against the serial Destra, we achieve 39x speed up. So the point is that it demonstrates that GPUs outperform multi-core CPUs for the single source shortage path problem. In conclusion, our solution advanced state-of-the-art on GPUs. And the key to high performance is to perform high-quality work scheduling. Our multiple write and multiple buffer design provides a mechanism for better concurrency. And our many bucket scheme provides a mechanism for better work efficiency. And the data setting scheme is essentially to provide a policy for using the 2 mechanisms. That is to find the optimal trade-off point between concurrency and work saving for a given graph type. For this reason, our solution works for many graphs. And finally, the decoupled manager is to make the high quality work scheduling technique efficient. And the key idea is to amortize overhead and reduce synchronization. And this concludes our talk. Thank you for watching.